Hello everyone, welcome to Simplilearn. This is Rakesh, your host and a consultant for today's session and for the batch too. Guys, your trainer is already in. Can we get a quick confirmation in chat if I'm loud and clear to everyone, and we shall get started from there. Okay, great. Thank you so much, guys. Let me go ahead and welcome Monica. Hi, Monica.
Hi Rakesh, how are you?
I'm doing good, Monica. How are you?
I'm good, thank you for asking.
No problem. Over to you, Monica. I think I've already shared the access with you.
Thanks a lot. Hello everyone. Good morning, good evening. Hope everyone's doing good today. You guys are having a good weekend, and for those of you joining from the US, you guys have a long weekend, so must be plans for enjoying yourselves and taking a break. Okay. So for today, we'll resume from where we left off last week. We had started to look at Dockers and, what are Dockers and uh, the different operating system environments where Dockers are used or can be used. And we did look at Docker for Linux, and this is how originally Docker was created as an application for Linux, and it uses the kernel container functionality of Docker. You require at least a 64-bit installation of Linux using the kernel version 3.10 or above, and it's available on most of the popular Linux distributions as a RPM or an APT or a binary version. So we did these slides. I'm just recapping a little bit for everybody to recall and remember where we were. And then, of course, we have Docker for Mac operating systems. Docker runs natively on Mac OS X under the Xi hypervisor. We saw what are hypervisors in our last class, and Docker is available in a DMG package, and it can be installed on any Apple computer 2010 or later, or your new Macs, and it requires an Intel MMU and EPT support and at least 4 gigabytes of RAM. Then you have Docker for Windows also. So again, Docker runs natively on Windows, and it does require a version of Windows 10 Pro or Enterprise, and runs on the Microsoft Hyper-V hypervisor. You also have something called the Docker Toolbox. So if your computer by any chance doesn't meet the requirements to run Docker natively on either Linux or OS X or Windows, another option that is available is the Docker Toolbox. So again, Docker Toolbox requires a 64-bit operating system, and this is essentially a local installation, like a application installation of Docker machine, a client program basically to control the Docker daemon and the local virtual box. You have a little diagram here. You guys can refer to this. Um, the local virtual box and yeah, and a version that is compatible with your your VM box. So once it's installed, the Docker machine um, can be used to control remotely installed Docker systems and Docker engines. Let's look at a little bit into the architecture of Docker. So Docker does use a client-server architecture, and the architecture basically includes a client, then you have a server, and then you also have a registry. And this registry is similar to, as you guys must be familiar with Windows registry, like any program you install makes an entry into the Windows registry on your computer. So it's a similar kind of registry. So your client is the primary user interface that communicates using REST API, works over HTTP, and also over local Unix socket. And your server is basically your Docker daemon. So you see this diagram here. So this is your client, your Docker client, and then this is your server, your where your Docker is hosted, and the server or the Docker daemon, what it's called, is essentially responsible for building, running, and distribution of all containers that you would create using the Docker. And registry basically, is responsible for storing all your Docker images. Okay, you can have a private registry. You can have registry with any other vendor. Docker Inc. provides a Docker Hub registry, for everyone in the world who wants to use Docker and wants to utilize that. And with Docker Hub, they provide a lot of Docker images that you can use to, create different containers. Let's look at a little bit about Docker images and containers. Okay, so we did go through an image last time in our lesson 1. What exactly is an image and how virtual machines or desktops and laptops get made using those images. So Docker images are a very similar concept. So it's a simplified version of your Linux operating system, and there are quite a few reasons to make this layer as small as possible, and any changes to this minimal set of Linux layer get captured as layers to the UFS. So remember we saw last time, let's look at this particular diagram only. So you have your kernel. On that you have a Ubuntu image, your base image, and on top of that you have added Emacs, and then you have added Apache, and you can keep adding on things on top of this. So this Ubuntu is basically your Docker image, and it has these images usually are very small, and to begin with they have very essential bare minimum base image content. Of course you can keep adding things on top of these as per your requirement, but to begin with these are created as base and bare minimum image of an operating system, so that way they are lightweight and they don't take a lot of time to download and launch. And it also gives you the flexibility to install whatever you need for your work, for your code, for your organization, to be able to install on top of that. Then next is your Docker containers. So Docker containers are your running operating system environments. It will essentially have a a host operating system environment. All the information about that, your different networks, how you're connecting to this. Any other programs, environment variables for this particular box. And Docker containers can run Docker images, uh, like you see on this particular diagram. They can run Docker images immediately, or they may follow set of instructions to do further customizations at the boot time. Basically when this particular machine goes up and running. So for example, we created a virtual machine last week when we did our first lab. So today we will run quite a few Docker commands on that. We'll download Docker images and run containers using those images, and we'll look at a whole lot of Docker images, commands today, not images. Then a little bit more about Docker images. So like we said, if like we saw in the previous slide, the base image usually of an operating system is a very lightweight image. It is complete. It is a complete operating system, but it's a very lightweight, least required basic image. And you can build Docker images in layers. We saw in the previous slide also. So each layer is like a file system. These images get created one layer at a time, and if depending upon how you plan, many of these images you put on top of your base image can be shared also. So in this diagram you see, there are like 1, 2, 3, 4. There are 4 layers, under the installation of Java 6, and the branching of the images of the image construction with 2 separate application installers. You have your My App, and you have another app which uses Java 6 layer that we have installed or built on top of this base image which we started from. You can create Docker images interactively by executing Linux commands, or you can even use a Docker file to create a Docker image. And we'll look at both of these, creating images using Docker commands, and also creating your own image using a Docker file. So Docker file basically, has a set of commands and instructions that you want to use to build your final image. Like you start with your base image, and then you want to install something else, you want to install something. So it's like, look, think of your Docker file like a batch file, where you give a set of instructions to be run. And these instructions are basically to create your image. I mean, I just gave an analogy of a batch file because that's what how batch files work. You basically list a set of instructions that you wanted to run, or tasks you wanted to run, and then you kick off the batch file, and it does all those in the background and come back and return you whatever you expect it to. So Docker file is something similar to that. Both of these are ways of creating your Docker image. Next is how to run a Docker container. So it's pretty easy to run a Docker container. All you need to type is the Docker run command and the name of the container. Docker will, first look for that copy of this particular image locally, you know, and if it doesn't exist locally, then it'll pull enough layers to fully put together the named image, and it'll pull it from your Docker registry. So the default Docker registry is your Docker Hub registry that is provided by Docker Inc. So once the image is obtained, the container gets constructed, and the included file system adds an added read-write layer on top of that. And a network interface also gets created and is also assigned an IP address. And if you specify standard input output and even an error stream, these are then used to connect to the container, and finally your specified application gets executed. Okay. We'll be running all these commands shortly, so don't worry. Once you see them being run, a lot of these things will be clearer. I know learning Unix commands just by reading text sometimes doesn't help you think of how the results will look like. So as the Docker container will appear as the child of the daemon process. And this is your Docker daemon. And now let's look at pulling and running the containers. So the Docker's process of fetching and running containers includes two steps. There are separate commands for each of them, the pull and the run command. So a Docker image must be located on the local computer. If it is not, then the pull command will basically cause a search for the image starting locally and then from your Docker registry. And then the Docker run command basically creates and initiates a container based on the image that you have selected. We have an example here. You're basically pulling the CentOS image, the latest version. The colon latest indicates that you want the latest version of that without mentioning a version number. You can also mention the version number here. Instead of latest, you can mention 1.4.5. whatever, that also you can mention. And if you do not mention anything here, then by default, Docker pulls the latest image. And then you have the Docker run CentOS latest image. Who am I? Basically, once you will run this till here, it will launch your container. Then you can run commands like who am I, present working directory, date, etc. It's a question. Where does the hardware layer end in this scenario? I think you're talking about this. So this is where your hardware layer ends. Okay, so yeah, we were looking at, so these are the different commands that you can run once you are in the container. And we'll be doing all of this once we get to our lab. Next is basically you run a container interactively so that you can pass it certain instructions, certain commands. And we've seen in the previous slide that Docker containers can be run interactively using the Docker command line tool, and you can use the -I or -- interactive switch to keep the standard input stream connected to your container, and you can use the -T switch to allocate a sudo tty. With these switches, you can run the container, and we can have our terminal session directly connected. And you see here how to run the Docker command using these switches. So we saw Docker run in the previous slide. Now we see a Docker run -I -T CentOS latest. And when this container is run, we want it to launch the bin bash program. This is what it means. Basically, open the shell, the Linux shell command. This is the command to list all your running containers, Docker ps. This will basically give you a list of all the containers that are running, and the stats command basically shows the running container resources. It gives you a whole bunch of information about all the containers that are running. You can also name a container. On the previous slides, we saw this instruction. We did not give any name to our container. We let Linux decide on the name. If you do not give a name, then Linux comes up with some name to that. However, you can give a name to your container. And yeah, give an example here. If you do not give a name, then Docker comes up with funny, comical names. Most of your Docker commands accept the name or even the ID of the container. And once we'll run these commands, we'll look at what is the ID of the container. So here we are doing a Docker run interactive TTY. Okay. Can everyone hear me fine? I just saw a message that my voice was breaking. Now is it better? Yeah. Okay. Thank you, Shikha. Yeah, so we're again going back and building on that same Docker run command that we saw in the previous slides. And -I thing we saw, we are running it in interactive and opening a TTY. Then you have the -- name. Okay, and you can give the name to your container. So we're calling this container as CentOS. Image is CentOS latest, and once the container is launched, we want it to open the Linux shell command. Then you have a command to stop the container, the Docker stop, name of the container. You can give the ID of the container here also, which if you do a Docker ps, you will get the details of this particular container, and that Docker ps command will give you the ID also. So you can use Docker stop, name of the container, or ID of the container. The ps command also accepts a -A switch for all the containers. So the Docker's ps command only gives you a list of running containers. But if you do a Docker ps -A, let me try to write it. Then it will give you a list of all the containers running or stopped. Okay. And then you have a Docker rm CentOS. This is basically command to remove the Docker, the container, sorry, not Docker. Next, let's look at attaching the running container. So Docker basically lets you create attachments to your running containers, and you can basically use one terminal on a computer to run a Docker container in an interactive mode. Remember, we just saw this instruction on the previous slide, creating container named CentOS from the image CentOS latest, and we are running it in interactive mode, and we are launching the Linux uh, shell command. So you can basically use one terminal on your computer to run a Docker container in an interactive mode, and then you can run different commands on it, like password, who am I, present working directory, and all. And on the second terminal on the same computer, you can use the docker attach command to basically attach the terminal to the container. And we created the container named CentOS, and in another terminal we ran the command docker attach to CentOS. So it will go and attach to this CentOS container that we created on our first terminal. And these are Linux shell terminals that we are talking about. We'll be doing an exercise on this. So for now, just try to imagine that you have two Linux command shell command prompts open, and you're doing this on one and then you're doing this on the other. So once you attach yourself to this container, if you do a date, present working directory, who am I, it will give you the information from this particular container. Yeah, so now this way basically you can attach two terminal sessions to this same running container that we started here. And then you are able to stop a running container, of course, and Docker allows us to do that using a Docker stop and the name of the container, ID of the container, whatever you want to use. So when basically your Docker stop command is issued to a container, a named container, the process that is running within the assigned process ID, PID1, will be sent the sig term instruction. And if the process does not end within the default timeout period, which is 10 seconds, yeah, it's written here, the process will be send the sig kill command. So sig term is the terminate and sig kill is the kill command basically. And you can specify different timeout periods also, by adding a -t or a -- time switch, okay, while executing your stop command. You can pause a running container as well and see docker pause. So this is again the same command. You're running a container, CentOS, image CentOS, and on the second terminal, you can go and pause this particular container. And of course, you can then unpause it also. And then this not paused, you can go and run all these commands in the Linux shell terminal that we are launching from here. So basically, behind the scenes, what happens is when you issue a pause command, all the processes that are running in that particular container get suspended. They are suspended. So this particular command works at the level of Linux C groups that we discussed last week. and the processes are not aware of the suspension and are not sent any operating signals as your sig stop or sig continue. The Docker container then can be unpaused, and the Docker processes any unfrozen and unfreezes using the Docker unpause command. And we've seen how you can do this using two different containers, terminals, sorry. So how do you start your container? So after the Docker stops a container, it still remains available, okay? It doesn't disappear because you just stopped it, you have not removed it, you have not killed it. And we saw the ps-a. Is container like a VM, and is Docker like something that is hosting a lot of VMs, containers with, wait a minute, there's a question. Mm, no, container is, so this is, let's quickly recap this particular slide. So Docker is a very lightweight software container and containerization platform. So if you look at this particular diagram, this is how our environments used to look at before we used Dockers or before we used containerization. We used to have our development environment, test environment, and your production environment, and different servers for that. And then, we used to have our code in our source control systems, and all the corresponding configurations and configuration files. And then different softwares used to fetch this code and combination of code and configuration files, and do our deployments on different environments, right? Deployment, packaging, build, everything, all these different software tools will fetch this code and then deploy it on our different servers, different environments. Now, with Docker, the change is you take this code and you build it in a container, in a box. Imagine this to be like, you've seen, you guys are aware of the movers and packers, that they use containers to shift your household stuff from one place to another. Usually they have a container on top of a truck, and once they load all your stuff into the container, they lock it for you, they seal it in front of your eyes, and then that container shifts to the location that you're now shifting to on top of that truck. And uh, if you are already there, where the container needs to be downloaded, then they bring it directly there. But for example, if you're not there, then they basically pick up that container, that box. So container is basically a huge metallic box. They basically pick up that box and keep it in their storage for you till the time you reached your new location, and then you tell them that, okay, I'm here, now bring my stuff in for me. So it's a box that has your entire house. Okay, if you are, for example, if I'm in Gurgaon and I have to move to Bangalore, I build my house in Gurgaon, and then I go to Bangalore and I build my house again. This is basically how we used to do deployments and software development before Dockers and containerization used to happen. It was like building your house every time in every environment. Some environments, the house used to get built very stable, very sturdy. Certain other environments, it used to, start shaking, and things used to start falling apart because, those server configurations used to be different, or, some file or some particular parameter doesn't work the way it was working in my, development environment, and it's not now working in the testing environment. So when you're ready to download your stuff, your household stuff in the new location, you basically get that container over to that location, and they take out everything that you put in the container and help you set it in your new house. So look at the Docker and container in exactly the same way. So Docker is a platform that, is a software. Okay, let me not confuse it with terms. So Docker is basically a software that helps you create these containers. And now you have a container which is, based on your Linux, Ubuntu, let's say, or CentOS. Let's go with the example of what is there in our slides. You start, because when you're moving houses also, you ask for a certain size of container. I have a 3-bedroom house, so I need a container that can fit a 3-bedroom house, household stuff. Or I have a 2-bedroom house. The same way. Uh, when you are building containers here, you start with a basic specification, basic setup, that my development environment is a Windows 10 environment, and it has all these softwares installed on it. And on top of that, my source code in a build will be executed and run. Or my environment is a Linux CentOS environment, and on top of that, these are all the other softwares that I'm going to be installing. This particular container of the CentOS container will talk to SQL Server. It will talk to some messaging queue server. And think of all these. You can think of these softwares as other containers. So you basically have all these boxes, and these are containers. Okay, so this is my box where my code sits. This is my DB, where my DB sits. This is some other app, that I need to connect to. And now these containers can talk to each other, like passing commands and parameters and instructions between different softwares, between different tiers of a software. Okay. Now the advantage with the Docker and containerization is that I just take this particular container and deploy it to my different environments in as many times I want to. I have written my code here, deployed on the development server, did my unit testing, then I deployed the same container. Now the metaphor that we took earlier of those movers and packers containers, just imagine that, the same, your household stuff, you put it in development, then you put it in testing, then you put it in production. So the environment doesn't change. You don't have to set the environment again and again. You don't have to set the environment variables again and again. You don't have to configure the environment again and again. There's an underlying hardware, for example, your development server will be a smaller server, like it will not be like your production. However, you landed your container on this, and then your test server will be a slightly bigger. You have landed your container on top of it, and then your production will be even larger. You landed your same container, the same thing. We are moving from, okay, we took it to our development environment, we did our testing, we fixed bugs, we built, we deployed, we kept doing that, over and over again till the time we were ready to, put it for, let's say, performance and user acceptance testing. We took this container, put it on the next box, test, fix bugs, test, fix bugs. And once we are ready, that everything is done, everything looks good, we are going to go ready to go live, you take it and put it on your production hardware. So here also the hardware is Linux, here also your hardware is Linux, here also your hardware is Linux. And your hardware, by hardware, I mean it could be a virtual machine, it could be a physical server, whatever, if you're doing a cloud deployment, that could be a virtual machine. If you're doing old-fashioned way deployment, then it will be a physical server. Okay, and in order to create these containers, we are using these different Docker commands, because Docker is the software that is helping us create these containers, these boxes, the movers and packer boxes. And all the Docker commands that we are running are to manage these containers, creation of these containers, running and stopping of these containers, networking of these containers, attaching these containers with other containers. Okay, does that help understand, containers and Dockers? Because this particular step is very, very important for you guys to understand. If it will not be clear, then all the further topics that we'll see, not just the Dockers lesson, but even the further lessons that we'll see on automation and CI/CD, there'll be some level of confusion. So please make sure you understand this concept of Docker and concept of containers. Docker is just a software that helps you create containers. Are there any other questions around this particular topic before we move on? Because I really want you guys to get this concept clear very well. Narendra, does this help answer your question, that you had? Good, good, good. I Okay, if there are no more questions, we'll continue from here. We did okay, we did this, we did this, we did. Yeah, so we were here. Next is basically starting your container. So once you stop a container using the stop command, which we saw here, then you need a start command to start it again. So yeah, we saw the ps minus ps hash a command will show you a list of all the containers, whether they are running or they have been stopped. Okay, now we saw there can be two possible states of container. It could be running, it could be paused, or it could be stopped. Okay, so if you'll do a ps dash a, it will show you containers in all the states. If you'll do docker ps, it'll just show you running containers. So you use the docker start command. Is it possible to do the practical? Vidya, when we'll do the lab, we have a lab coming up. Then I would highly encourage you guys that you also do that simultaneously. At least run all the commands that I would run on the shell prompt. That you also I'll come to your question, Sonali, in a minute. So don't do it now, because I want you to focus on the commands and listen to the commands, what they do and what they are used for. However, when we'll do the lab, I would say you all open your VM, open your Linux shell, and run those along with me. So there we can go a little slow also, that so that you all also get a chance to run that and do that. Okay. Uh, Sonali, to answer your question, in case bug fix is done on testing container, then do we move the container to development container? Yes, you should. You should. Basically, if your container has basically moved from development to testing, and you're saying you're going on fixing bugs here, and your basically your container is changing every time. Your not your container is not changing. Your application footprint is changing because you're fixing bugs. Yes, as a good practice, you should also keep your development containers in the same state as this. But don't worry about this so much at this point in time, because remember, we are also going to be using source control, some kind of source control system you will have. So basically all your changes that will be happening because of your testing bug fixes will be going to your source control. And there are softwares and tools in the middle, that do the build and deploy for you. So that same software will do the deployment on your testing environment, for example, after bug fixes. It will also do it on your development container after the bug fixes. Okay? Yes, the answer to your question is yes. You'll have to, yeah, you can start the container again. Yes. Shrikant. So Sonali, does this answer your question, what you were trying to ask me? Okay. So yeah, this is basically your command to start the container that you have stopped. And the dash I switch is a interactive standard input switch, and the dash A or the attach switch, you can attach uh, a standard input or a error stream to your container. If you guys, though we'll be covering containers to quite some extent in this particular course, but if you guys want to read more about Docker and containers, there's a very good book called, wait, there's a very good book called the Docker book. It's very good. If you want to really understand Dockers and containers, I think that's the most simplified written book available in the market. There are like hundreds of books available on Dockers, but the Docker book is, I personally find it to be very straightforward, very simple, and very easy to understand. Because if you're basically trying to learn a new topic, you want it to be easy to understand. The person who's yes, James Dunbo, yeah, the person who's explaining should explain it in a very simplified language. Of course, Docker and containers will continue to be what they are. They'll remain to be what it is. But this book is pretty good. It is there on Amazon. It is available as a online read-only copy also, and it's not very expensive also. I think I purchased it for 300 or 400 bucks. I have a Kindle version of that, so you can download that and just. Is there any limitation of number of containers? No, there isn't really, Sonali. There's no limitation per se. Okay. Okay. Next we have something called removing containers. So you can basically remove the container using the rm command. Removing means removing. You're completely getting rid of that. So any container that has been stopped can then be removed also from your local hosting computer, and you use the docker rm command. So this command will basically discard the named container, and any changes that you have made to it in its read-write layer in the union file system. Remember, we saw you keep adding layers on top of those, on top of your base image, and these could be different read-write layers. So once you do a docker rm and the name of the container, you're basically discarding all those accumulated changes. And you can also use this particular command So this is basically your Docker PS command that we've been looking at all this. Wait a minute, let me clean this up a little bit. The Docker PS, this command we've been seeing earlier, this command basically uh, gives you a list of Dockers, running stop Dockers. So in this command, basically we have, um this is like, spawning a child process, with the Docker PS command. So it will basically return all the identifiers of all the stopped containers. Docker PS -a gives you a list of all containers running and stopped. AQ gives list of all container IDs that you want to be removed. So basically you're giving this as a sub command to the Docker RM command. So this will give you a list of all container, and that will feed into the Docker RM command. So this, you use this command when you have a whole bunch of containers that you want to remove. If it's a single container you want to remove, then you use something like Docker RM, name of the container, ID of the container. But if you have a bunch of containers that you want to remove, then you basically use something like this. Everything that is here, basically get rid of it for me. Okay. And then you finally have something called a daemon container. So Docker can also run containers as daemon, and daemon or detached also it's called, which are uh, something like continuously running processes, and you use the dash D or hyphen D switch with the run command to start a container in detached mode. And a daemon process is something that runs in the background, just for you guys to know. It's a process that you spawn in the background. That is what is a daemon process. And here you can see the container uh, run, Docker run, daemon, name is web server. We've given the name to this container, and we're using the image nginx, and we're not giving anything after that. So we just want this particular image to run as our web server in the background. This is what this instruction will do. And to stop the detached running container, you use the Docker kill command. This will basically stop the container, and however, it will retain its state, its accumulated state. It will not get rid of that. It will not destroy that for you. Okay, so here we have a lab. Now, if you guys want to run these commands along with me, you can open your virtual machine. And we'll is it possible? Can you use Microsoft instead of Google? Ritesh, actually all the labs for this particular course are on Google Cloud. You guys can alternately do is do the same labs as homework on AWS. We already created VM on AWS last week. So some of, like, all the Docker commands you'll be able to run, not a problem. Some of the future labs you might not be able to do on AWS because we have our lessons available here on. Actually, we can download on AWS also. It'll it'll not be possible for us to do both in the class because we would not have so much time to do our labs on Google Cloud and AWS too. So maybe you guys uh, should try to do this on another cloud environment on your own, and we'll do this on Google Cloud in this course. Yes, yes. Yeah, yeah, yeah. These commands have nothing to do with your, cloud environment. It doesn't. These are generic, basic Docker Linux commands. So anywhere you can have a Linux virtual machine, or even if you have a Linux box of your own or in your computer, and you uh, install Docker on that, you'll be able to run all these commands. So these have nothing to do with that. These work only on Google Cloud. There's a question before. You said that or something. Does the Docker container have any dependency on the underlying infrastructure, or can a container run anywhere? Container does need an underlying infrastructure, and Docker containers are to be built on the same operating system as your underlying infrastructure. So if your virtual machine is a Linux Debian, you'll not be able to run a Windows container on that. So you'll need to have a Windows VM to run a Windows container. And you'll need to have a Linux uh, underlying infrastructure, a Linux virtual machine, to run any kind of Linux uh, containers. The container version doesn't have to be the same. Like we created our VM Unix on Unix Debian, but we'll be doing our labs on other versions of Linux. So that is not a problem, but it has to be the same operating system. Okay. So let's begin with checking the version of Docker. So we have Docker 1.12.5 and this particular build number. So we have a public Linux registry available called Alpine. We will pull that particular image down from the registry and load it on our repository. We saw the command docker pull and Alpine. Since I did not mention any tag, it will take the latest tag and it will pull the image for us. Let's see what we have in images. So Docker images will give you a list of different images, and this is the Alpine image that we just pulled. And look at the size of it, 3.9 megabytes. It is an entire operating system, 3.9 megabytes. Can you let me know the image deployed? Which image, Vidyasagar? Can you rephrase this question for me? We did not dip the Linux or it was Debian. Uh, remember when we did our first lab, we created an operating system using the bucket we created, and that bucket had two versions of Debian, and we said we'll use the latest one with the latest date, and we created our operating system using that bucket. Please try to do these labs offline, guys. Whenever you get time during the weekdays or on the weekend, try to do these labs offline. It'll make it easier for you to keep the flow, and you'll remember. Once you'll do it yourself, you'll remember more, because otherwise we talk about so much here that it's hard to remember everything just by listening. So try to do these labs offline. Okay. So we just saw the Docker images. We saw the Alpine image that we just uh, created. Now let's run this image. So am I writing here? Docker run. Let's give a name to this. Let's call it client, and the name of the image is Alpine, and we wanted to run uh, the shell command. So let's look at this command before I run it. So we added the parameters TCY or terminal interface, and we added the input stream, and we gave the name to this container dash dash name. Name is client, and that's the name of the container that is running. This is the image. This is the image we just pulled earlier here, Docker pull. This is the name of the image from which we want to create this container. And once the container comes to life, it'll put a read-write layer on top of this image. And when it comes to life, we want it to run the /bin/sh, which is the Alpine shell. Now I'm going to run this. See how quickly it came to life. Okay. For virtual machines, also take some time to come up. For all of you who have worked on virtual machines or have seen virtual machines being used, this is not how quickly a virtual machine comes up. That's basically, a big benefit of these containers. Now let's run a few commands on this. Let's ask the date. Let's ask present working directory. Who am I? I'm root. Okay, perfect. This is take us to the root directory, and yes, we are in root. Let's create a file, and you basically use the command touch to create a file. We'll call it test file. So let's see what we have. We have this test file that we just created. It is the size is 0 because it doesn't have anything. So we have not created, we have not written anything to it. Now let's exit this, and we're back to our. Let's do a Docker PS. There's nothing here. Let's do a Docker PS. Oh, so this is the. Wait, let me clear the screen. So this is the container we had launched. Remember, Alpine name was client, and we asked it to trigger the bin bash command once it came to life. However, we exited it. It says that you exited 24 seconds ago. And so if you'll do a Docker PS, you'll not see this because it's not running anymore. However, if you do a Docker PS-A, you'll see all the containers. So this is the container ID that we were referring to during our slides, that you can stop, start a container, pause a container using the name or the container ID of that. So this basically, this container has its own identifier. It's based on your Alpine image and has the name called client. However, we stopped it. we are pulling these images from Docker Hub. Remember, we saw Docker Inc. provides a registry, a global registry free for anyone to be used who wants to use the Docker software. So we pulled this image. Remember when we saw the Docker pull image command, we were learning that. We saw that first it will look at in the local, let me go back to that slide. The Docker image must be located on your local computer. If it is not, then it looks for the Docker image in your registry. And if it is not there anywhere, it will give you an error. It will not create a container. It will not pull that image. It will give you an error. Okay. So the Docker software is in the, yes, the Docker software is in the Debian image that we use to create our virtual machine. I was about to tell you this only. So yes, you're correct. Okay. If you build your virtual machine with a Linux, now you with a Linux version that does not have Docker, then you will have to install Docker first. But okay, we'll go back to our lab. Where am I? Okay, so we just created a container, but then we stopped it. Now let's restart it. And the name we gave it was client. So okay, now let's look at list of, so now we have it here. Now we can see it in this because it's a running container. Okay. Now let's do a Docker attach. You see, this is the test file we created using the touch and file name when we first ran this container. We first ran the container, we created this file, we came out of the container, stopped it, then we restarted the container, name client. Now we attached to that particular client and we see that file, our file, still exists. We have basically rejoined the container and we are able to see the state that we created and it is still there. It is existing. Let's come out of this. Now let's look at the other way example, a counter example. Let's create another container. So Docker run this command we used earlier also. I'm typing these as many times as we need to do the lab so that you guys get familiarized with it more. I will not go use the up arrow key and as much as I can. Okay, let's create a client 2 this time. Again, using the same image. Let's see, present working directory is root. Nothing in there. Let's get out of this and do a Docker ps. So this is our client 2 that we just created and exited, and this is the client that we had earlier created and exited out of that. And now we have two list of two containers, and they're both created from Alpine image. However, they have a different name. They are also running the same program, the Alpine shell. So we have two different states. Now let's look at removing these containers. Remember, we saw the command to remove a container. Docker rm client. This is the name of the container, and Docker rm client 2. Now let's do a Docker ps, and nothing is there. Okay, we removed both the containers. Now let's pull another image. Docker pull. This time we'll do a hello world. Let's do Docker images. So this is the Alpine image that we pulled some time back, and this is the hello world image that we just pulled. We still have the Alpine image. Remember, we only removed the containers. We did not get rid of the image. The image is still there. Okay. And now we also have the hello world image. Let's run it. Docker run hello world. Okay, so this is basically what this image does. It says hello from the Docker. Now let's look at the images again. Okay. Interesting thing to see is the size of these images. We already, when we downloaded the Alpine image, we saw it's like under 4 megabytes, and Hello World is 1.84 kilobytes. So, these are really, really small footprints. Okay. Exit. No, not clean, clear. Okay. Now let's do a little bit of cleanup after us. So let's do a Docker ps. See, there is one. So this is basically returned all the identifiers of all the containers, and we see there's one. So this guy must be the hello world, because we removed the containers that we launched using Alpine, remember? So this guy must be hello world. So let's do a Docker rm Docker ps. Remember, this is the command we saw. Docker ps aq basically gives us all the container identifiers, and we feed this command to the Docker rm. My -f is forced, so it will force remove all the identifiers that this particular command will return. Oh. Okay. it's gone. Okay, we just removed the hello world container also. That's why if I do a docker ps aq, I don't get anything now. This Now let's get rid of the images also. So we don't have any images. Anything we pulled for this particular lab, we've cleaned that also. This is these are basically all the instructions commands. Of course, you guys can try, pause, restart, all of that. You can try on your own. Now you know how to pull an image from a registry. You know how to run a container using that image. You know how to give a name to your image. Again, you know how to launch a shell prompt. You know how to create a file. And there's a question. Is there any extension to image? No, images usually don't have any extension. You mean like the Windows file kind of extension, right? No, they don't. They don't. So you guys can keep trying as many commands, different commands. You can keep, trying to download different images. And further in our labs, we will be downloading, we'll be pulling a lot of images. We'll be pulling images of, databases, of different softwares and tools. So we'll see a lot of that. But, keep try out all different commands that we learned. Okay. So this was basically our first exercise. Let's do a knowledge check question, which is what is a Docker image? Yeah, it is basically a read-only template containing a complete software application. Good, you guys understand now what a Docker image is. So good, I'm happy. Now we'll look at working with Docker images. So as we have seen till now, Docker creates running containers from Docker images. In this topic, we'll learn some more about creating images, storing images, storing them for distribution, search it for images. So the Docker project from Docker Inc., the company, basically hosts a registry and repository called the Docker Hub. That is where we were pulling the images from that we earlier pulled. Okay, the Hello World was a local image that is being provided by Simplilearn for this particular exercise, but it basically it could be anything. Okay. So this registry essentially contains different versions of Linux distribution that you can use as the base layer for any image. And we used the image CentOS, you remember, in our previous lab. And to build a Docker image, we basically start with a Linux operating system base and then keep adding layers on that one by one. This can be done interactively by running a Linux distribution and then simply executing commands in the container to make changes. And By doing this, you're basically writing to the read-write layer that is added to the base image. Another way to build a Docker image is to place all the commands in a file, in a special file called Docker file. We briefly touched on this earlier also. And then run the Docker build command uh, to create the image using the Docker file. So in practice, we find that we use a combination of these two approaches. In real life, that's what you'll see. And we'll use the interactive build command to test out various ways of building a final image. And when we're done with that, then we'll place all those commands in a Docker file. And this Docker file then can be placed into a source code control and properly managed as a project artifact. And you can use the search command on the Docker Hub to basically search for your images. So to an earlier question, who asked that question? One second. Sonali, you asked this question. So basically, this is how you build your container for your software development, like you do. Yes, base image is essentially an operating system. It should the least be an operating system. It could be the operating system plus a few things with that. So yeah, that is the base image. So yeah, I was saying, Sonali, earlier you asked this question, where we took the example of a container and, moving that container to different environments between development and testing and your production. Okay. So this is basically, the underlying groundwork of building those containers, your images. And in practice, you'd be using a lot of Docker commands initially to create your images or your containers. And then once you have all the instructions right, or what all you need, then you basically take all those individual commands and put them in a Docker file. So it becomes like, a resource file for your project creation, and that Docker file then starts to live in your source code repository, because you don't want to go figure out that commands on every environment, because then again there's very little automation happening there. So once you have figured out your entire environment, then you put all those commands to build your environment into your Docker file. The Docker file sits in your source control, and anytime you need to create a new Docker image for your particular software development environment, or you want to use that image for building a future software development project, you could use it for that also. Okay, there are a couple of questions. I'll go through these in the sequence. If the container depends on the underlying infrastructure to run, why do you include the operating system in the container? Because these containers are, independent, fully sufficient by themselves. You should be able to take the container from box A of Linux Debian to box B of some other version of Linux, right? If you do not have a footprint of operating system in your container, where will the rest of your software sit if you move from one environment to the other? Then it will become your environment specific, your hardware specific, very similar to how we used to do things before Dockers and containers came to life. Does it make sense, Jack? Okay. So for deployment in different environments, just running Docker file, yes, essentially yes. To create your image, you'll run your Docker file. You'll not have to run those, 100 commands again uh, in different environments. You'll not have to go and figure out, and trust me, there are many times 100 commands to build an image. A real software development environment has so many commands to build an image. So yes, that would be accurate, Sonali. But it's the same set of commands, same set of software, same sequence of installation. So your room for error reduces. You're always creating your environment the same way, starting till the end. Okay. Okay. So we quickly saw the Docker and why are you small? Okay, let's go to the next slide. So some of the issues installing software. So softwares, when you're running a Docker container in an interactive mode, you can use the packaging system for that particular Linux distribution to make any changes. And depending upon the distribution you have selected, you'll probably either use yum or apt-get commands to do your further installations. Uh, this certainly also results in a lot of dependencies. Let's take an example. For example, if you're installing Java, and I mean we'll be installing Java in our future labs, so we'll get there. It usually brings in a large collection of other packages also along with it. So doing this, it creates a lot of dependencies that get installed, which you might need, might not need. Yeah, here's an example. If you're trying to install Maven using Yum, it pulls an open SDK 1.7 dependency which conflicts with Java 1. This should be resolved now. I mean, don't tell me it still happens. But yeah, who knows, maybe. So if you need to focus on developing very tight and integrated images, that have only what you need and they do not add a lot of unnecessary dependencies, which first of all you don't need, and secondly could cause conflicts and issues, with some other installation you have done. You may find that you can resort to using other methods to install software, like using tar or RPM or Dev Archive, or maybe even using source code and then compiling the software in the image. I mean, for people who are hands-on on Unix, do that all the time actually. So that could be a better way of installing, and we'll be mostly doing our further installations using this only. However, you can also do a yum or apt-get. Try these. You have a virtual machine. Try these commands, play around with these, see what happens. At the worst, if your VM gets messed up, just delete it and create a new VM. You guys know how to create VMs now. Just make sure you stop them when you're not using them, so that you don't use up your $300 of credit. Okay. Removing images. We already saw this when we did our lab. Docker images gives you a list of images. Docker RMI, name of the image, basically removes it for you. Now to adding packages. So the CentOS image that we used in our previous lab is a very cut down version of Linux, and it doesn't have certain Linux commands, even if config or which. You can install these using yum. So you've run a container using the CentOS image, and then you've installed which you've installed NetTools, and you've exited from there. So that's a way of adding packages to your underlying base image. So during the process of building Docker images, you may also need to perform some quick checks to see what changes have actually been made. And the Docker diff command will list all changes made by displaying a list of files that have been added or changed to your read-write layer. So we know this Docker run. We know what we did here. We basically added packages. Now you can do a Docker diff CentOS. So it will do a diff of present state of CentOS with this state of CentOS that we created the container. It will show you a list of all these things. It will show you that you've installed these two. Then you can do a commit that yes, I want this, or you can remove CentOS and then run it again, and you'll still have CentOS net on it once you run it again using this, since you have committed that you want the change that you've installed. Okay. In order to verify changes, you use the Docker inspect command. And you can use the -f switch of the inspect command. It will basically process your JSON file with your Go language templating system. The double brackets you hear is required by the tool, and basically sends the subcommand to the Go language for processing. And so here we just extracted the information about your chip architecture, which you can run and see what it will return you. I wish that, no. Okay, next is automating builds. So Docker image creation can be automated. We have already seen a way of doing that using Docker file. So once you have all your commands in your Docker file, anytime you want to create the image, you run your Docker file, and your image is created again. And for large-scale DevOps workflows, it is actually recommended to automate the building of your Docker images. Docker provides a build command for this purpose, and the build command should be executed in the context of a directory built to contain the information that is required to build an image. And the most important file in this directory has to be your Docker text file. And within the directory, you can place all artifacts that you need to copy into the image as the image gets constructed. And each command in the Docker file basically results in the creation of a unique image layer. So remember, we saw this, that we can keep building layers on top of this. So this is actually a pretty great feature. And when you run multiple build commands, you'll find that the earliest command in the Docker file doesn't get uh, executed again and again. Instead, the build command will find what was the previously created image layer and use it and start on top of that. Only when your build command will basically hit a new or a modified command will it actually do the work of building new layers all over again. So now let's look at creating a Docker file. So Docker file is a text file basically. It starts with the from command in the beginning, and from has the name of the base image with the version number. So your Docker file command always begins with from. Okay. And then you have the maintainer, basically, the name of the person who's created the Docker file, who's maintaining the Docker file, the email ID. It's like a notes. It's like a notes thing. Then you can have Docker shell commands, basically define the default shell to use. So you want it to use the bin sh, and it takes the form of shell and executable name and any parameters you want it to run. Okay, so this is your shell, this is your cmd command, and these are different parameters that you want it to pass to it. So this one is for Linux and this one is for Windows, and cmd is a Windows program. Okay, this all goes in your Docker file. Then you can have a copy command, so that will basically copy a resource from the directory in which your Docker build command is being executed. Okay, source files must be located somewhere within the context of this directory, in that directory or a subdirectory within that directory. And it is possible to use Unix shell wildcards to copy a group of files, like a copy jdk star.rpm to /dem. Okay. One thing to note is that the destination directory like this must always end with a slash. Okay. If the destination directory does not exist, then it will get created for you. Okay. You can have a add command that will basically copies files, any remote files that can be identified by a URL into the container. And as before, source files must be located in the context of the build directory, and files that have to be retrieved from a URL location should be specified. And the source file specification may include a Unix shell wildcard, like we're trying to add Apache Maven star.targz to /opt folder. Okay. One thing that is great about this is the local source files in a tar or any other compressed tar file automatically get unpacked by this particular command, and this can be convenient depending upon your approach to installing software. Then you have the docker run command. So that is basically um, the main workhorse of the build process. And this particular command causes the program to be run in the container that is being built, just as if you were entering this command in an interactive mode. Like you have a prompt available to you, and you just keep on. So here we are installing which. Remember, we just saw this yum install -y which when we looked at adding packages previously. So if you were to write the same in a Docker file, you'll use the run command and then run rpm, run cd to this folder. You can use the run command to run different commands. Like here we're trying to install which, and here we are trying to RPM. Here we are running these as separate steps, which will result in an image layer being built to reflect each change. So this will be one run, and then this will be another run. Okay. The last particular run command, let me clean this a little bit. The last particular run command basically separates two commands using a semicolon. See this here? This will make sure that the cd command and the ln command results in the addition of a single image layer. So this guy will basically add a layer. This guy will basically add a layer. These two commands will add one single layer. They'll not add two layers. Okay? They'll add just one layer. So you can concatenate two commands using a run command and a semicolon. So for people who know Unix, Linux could be a repetition, but we still need to cover. And then you can use the env command to set your environment variable, context variables, that is usable in the context of building this container. And it can be used to declare existence of an environment variable, which is set to a specific value during your Docker build process, or it can set the environment variable to the text string specified in a command. So here we are setting the environment variable called Java home to this folder, and then we are setting the path to this path. Then you have the cmd. The Docker cmd command is it's a little different from all the commands that we've previously seen. All the previous commands are directives, basically to the build process, and are executed in the order as the container is being constructed, and then are being saved as your final image. It's export in. What is export in image in Linux? Yes, yes, it is. It is. You can also use it as export, correct? Okay. So all the previous commands, environment, yeah, it is environment, but you can also use export on a shell prompt to set environment variables. That's another way of setting environment variables. Yeah. So all the previous commands basically are directives to the build process of your image and are executed in the order as your container is being constructed, and then they get saved as your final image. The cmd command basically specifies the program or command to be run much later, not during the build process. The CMD command will be run when the Docker creates a new container based on that particular image that you have created with all those commands in your Docker file. Okay. So the CMD command will be run when your Docker creates a new container based on this particular image, and then finally passes control to it for execution. And it's a great way to specify a default command to be run for an image. So the CMD specified program or command can be overwritten by the specification of the program during the Docker run command phase of operation. So this thing is very similar to, when we were, wait a second, when we were doing the, I hope it was there. We did it in the lab. Yeah. Remember when we were running this command again and again? So your CMD command is basically this, once your container is built, launched using this image, run this program, leave me at this program. So your CMD command basically does this. Okay, this is a command line command that is a Docker file command. They do the same thing. Okay. Command. Okay, so here we were. And then next is your Docker build command. So that is, your automated way to build Docker images. The Docker build command will read your Docker file, the text file that you have created. That should be located in the directory where Docker build command is being executed. And this directory then is called your build directory. So if you hear the term build directory, that means that is the directory from where you're running your Docker build command. So the automated process is driven by Dockerfile, but all the resources that you referenced by a Dockerfile must be located in your build directory, or files that are located in a particular URL that if you have specified that in your Dockerfile. The build process, it can be understood thinking that it creates a new container based from the image specified in the first command, the from command, and then executes all the later Dockerfile commands in a textual order. So like I earlier said, think of it like a batch file, like a Windows batch file we used to have. It had a sequence of steps, and the sequence in which we want those steps, those programs, those tasks to be done. So think of it like that. It starts with the from command, which is from the base image that you're starting with, and finally this container, after your entire Docker file commands have been executed, this container gets saved as an image that you're created using your Docker file. So this particular example shows the use of the build command that will create a new image with the tag CentOS Java latest based on the Docker file that is specified in the directory by this dot character in the end. Okay. So we'll be using this in our next lab to create a, not like, yeah. Let's go back to our shell. Let's create an image that contains a SSH server so that we run it in the background and we can make secure connections from our client to the container. So first thing we'll need to do is generate some keys, and we'll do that. We do not have any requisite keys. Okay. We've stored them in home student.ssh slash ID RSA, and I did not use any passphrase, so I just hit a enter. Now that the keys are generated, let's see. So we have our ID RSA public, both private and public keys. Since we're going to establish a secure connection, we need a private and public key combination to do that. So your ID RSA is your private key and ID RSA.pub is your public key. Now let's go back to our home directory and create wait a second. I'm going to make a directory called build, and we'll go to this build directory. Next, we'll copy the key that we generated, copy the public key, and we want to copy that to a file called authorized keys. So I'm going to use copy. Let's create a Docker file. We can create a file. What am I using touch. And now let's open the Docker file using the Nano editor. Now let's start editing. So remember, the Docker file has a number of steps that we will need to follow in order to create an image. And from our base image, Alpine latest will create that. So it's basically from Alpine latest. I want to run APK update. Then I want to run APK add open SSH. Nano editor, it's a Linux Unix editor. So this editor is a part of the Linux that we use to create our VM. Okay. You'll have some sort of editor. If not, you can install it. You can install any editor that you want. So next we'll add user, student, So first we ran the APK add in order to open the OpenSSH package. Then we added run add user student, and we ran it with a ampersand command, which basically means run it only if your last command was successful, and then make a home student SSH directory, and also echo student colon student and pipe that to ch password. Okay. Next, let's add authorized keys, home student. Authorized keys to home student. So next we basically added the authorized keys that we added to the build context at the beginning. We added that to the home student.ssh directory. Next we'll change some permissions. You can write these as lowercase also, but it's a good coding practice to write these in uppercase. I'll just go through all of these. Let me finish typing these. Okay. We changed some permissions here. SSH that way, is very particular the way we set these permissions. Otherwise, it will not run. Okay. Next, we ran the SSH keygen and typed type RSA, and we wanted that to go to SSH host, the RSA key. And finally, we exposed the port 22. The container will have the port 22 for a connection from outside. And finally, the command user bin, and -d is the daemon command. Okay. You'll have all these commands, in the lab lab files that you get. So don't worry, you don't have to, quickly type them now, or of course you don't need to remember them. Okay. Okay. I just exited the nano editor. Now we'll do a Docker build. Oops. So see, now all the commands we listed are being executed from Alpine. Run apk update, run apk add, run add user, password changed, add authorized keys, changed permissions, run SSH keygen, expose the port, and use the command user bin, and in the end it said successfully built. Let's clear this page. Now let's do Docker images. So we have our SSH image. Let's run it. We created it from Alpine, remember? Docker run. We'll use the -d command, which means it will run in a detached mode, run it in the background, and we did some port mapping. Remember, we exposed the port 22 from inside of the container. 2022 is the port that we are mapping to port 22 from within inside of the container. We'll name the container SSH, and the image will be SSH Alpine that we just created. Okay, let's do Docker yes, and that is the image we just built from SSH Alpine. Let's now try to connect to this. Now we are inside that distribution that we created. Okay, we'll exit from this. Connection to localhost closed. We'll stop SSH. Okay, we'll remove SSH. We used all these commands earlier. To the question here, why chmod twice, changing permissions twice? There were two different folders for which we had to give different permissions. That's why. Remember, we mentioned two different folders with different permissions. So SSH works in a certain way, you know. So your okay, good. So we'll remove. Oops. SSH. We'll remove the image. Okay. A lot of removals. Let's do Docker. Let's clean first. So you see, these are all the layers we had added to our image. You see this before I clean it? These are all the different layers that we had created to our image. So earlier when we did a Docker RM, it just quickly removed it, the SSH. Now when we did the image, it basically removed all the different layers it created. That's why you see so many deleted, 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 deleted. Had it been just Alpine, it would have been like one line and deleted. Okay? Why do I keep writing clean? Let's look at Docker images. And we don't have our SSH image anymore. We just removed it. Let's do a Docker yes. And we don't have any containers running. So this is the end of our second lab also. Now I'm going to leave the Docker file. Okay, anyways, I think we are ready to take a break. But this is how our Docker file was. Now you can look at it again, and you can keep adding things to this. Now you know how to add packages, how to add users, how to run different commands into it. You can just keep building. Just play with it. Take some time. Just if nothing else, pick up some Linux command from the internet. Google something for your environment. No problem. Get rid of. Hello. Why not? Okay. So all I was saying was try different commands. Worst case, like I said earlier, if you mess up your VM, delete it, create a new VM. At least you'll get your hands dirty to get comfortable with this. That'll be your, trust me, that'll be your best way of learning Dockers and containers and building Docker files and all that. Okay. At this. So there was a question, can you please explain Docker file once again? We'll come back from the break, start with that, and then continue with the rest of our slides. We'll take a break at this point in time. I'm going to open the poll. Please take the poll before you go for break. It's 9:41 as per my laptop watch. We'll meet back at 9:51. So I'll see you guys in a bit. Please take the poll before you go for the break. Thank you. Hello, is everyone back? Please confirm to me in the chat box if you're back from the break. Okay. I see Shrikant and Jack are back. Is everyone else back as well? Sitaram as well. Jack, for your that content related problem on the Simplilearn website, I was also asked to pass this message to you that you can call the help and support and just don't hang up till they fix your problem, because Rakesh has escalated it to them to have this addressed. However, maybe after the class you can follow up with them as well. And I mean, worst case, if it is not, again, drop a mail to Rakesh. He's usually very prompt at getting this resolved, and it's quite unfortunate that it's been an entire week and you still continue to have that same problem. Okay, okay, do so. Okay, is everyone else back? We're gonna get started, guys. So the last we left was a question from Shrikant too, indeed. Can you please explain the Docker file once again? And can you explain the commands inside the Docker file quickly after the break? Okay. So I have the Docker file open in front of me. So your Docker file is a list of all the instructions you will run to create your customized Docker image. Okay, we are talking about image. Don't confuse it with container. We're not at container yet. So we earlier saw a way of creating a container by pulling an image from the registry. Remember when we did the Docker pull? Now we are trying to build on top of those base standard images by using a Docker file. So we start with a base image. We start with Alpine, latest version of Alpine, and then we add layers, we add softwares, we add users, we add permissions on top of that. You can run all of these as individual Unix commands, Linux commands. If you go to your Linux shell command prompt, you can run each of these, one after the other on that particular image. But then every time you need to create that image, you'll have to run all those commands individually again and again. Instead, if you put all of those commands in the sequence that you want them to be executed in a Docker file, all you have to do is build your Docker file and you'll have your desired image in place. So you always start with your base image, and we are starting with the latest version of Alpine. Then we want the Docker to run an APK command. APK is the package manager for Alpine. And we saw all these, run, add, expose, CMD from in the slides that we were last looking at, remember? So next we want to run APK to add the open SSH package, because we are trying to establish a SSH connection. Remember, we created those private and public keys. So then we say run to add a user. Okay, we added the user student, and with a double ampersand command, which basically means, if your previous command is successful, then only run the subsequent command. So if you are successfully able to add user student, then go ahead and make this directory and set this password. So this is a way of concatenating commands. And so if this command, adding student, is successful, make the directory home student.ssh and echo this on your command line to see that your script is executing fine. So this is basically you can echo when you're building your image for your project. You can keep echoing, first step successful, second step successful, whatever you want, like more like comments. And we pipe that to ch password. Next, we wanted to add authorized keys. We created these keys before getting into the nano editor. We created these keys. So we added the authorized key that we added to this build context folder. Then we add that to your home student dot ssh folder. Okay, this particular directory. Next is we need to change some permissions for student. Chmod is for chmod is the permission where the owner has read, write, and execute permissions, and chmod 600 is where the owner has read, write permissions. So we gave these permissions to these folders: home student SSH and home student SSH authorized keys. Okay, and this is required because this is how SSH will let you make a secure connection, otherwise it doesn't work. So these are some of the parameters, some of the prerequisites you need to have in place in terms of your folder structure, folder permissions in order for the SSH to work. Next, we did run the SSH keygen program and type RSA, and we wanted that to go to SSH host key, host RSA key, SSH host RSA key. Okay. This is where we are establishing your secure connection, your RSA key to your host. And then we are exposing a port number 22, which once your container will be run, once your container will be started from this image, it will be connected on the port 22. On port 22, we'll establish that secure connection with that. And lastly, we are giving the cmd command, which I remember I showed you when we were doing our Docker run. In the end, we were telling it once the container is up and running, which program to run. So this is your cmd command, and we are asking it to run the user bin SSH in as a daemon program, as a background program. -d is for that. So these are all the commands we wrote in our Docker file command. Student user in double quotes is like a comment. Every time you write a batch process file, or you run every time you write a file that includes a lot of steps and a lot of instructions, you write some kind of commands, comments. You write something that it should return to your input output stream. Basically, some comments it should write to tell you that that the execution has happened, the execution is happening. So the student user, basically, when you'll run the Docker build on this Docker file, this will show as comments. Student user, student created with password, reset password, all this. So these are basically outputs for you to see what your Docker file is doing, how far it is reached. This is a very small Docker file. When you create Docker files for your projects, they'll not be so small. They'll be huge, large files. Okay, they'll not be so small and straightforward. We're just taking an example here, right? Okay. Let's move forward. We have a knowledge check question. Why do changes have to be made to containers rather than images? Yeah, the right answer is all of the above. Your base images are always read only. You can build layers on top of those, but you cannot change the base image. Okay, next we have registries and repositories. So we did talk about Docker registry earlier. So Docker, easily lets you create running Docker containers based on images. Maybe my question is wrong, but the individual Docker commands were to create and run container. However, in Dockerfile, we're doing something different. What are we doing different, Sonali? We are taking a base image, we are building on that base image, and we are using that base image with additional builds to fire a container. You can do these as individual commands. You can do these in a Docker file. And end of the day, you need a container to be run based on that image modifications that you have done. So we're not doing any, this is not different, it's the same thing. Why you are feeling it's different? Dockerfile has the same set of instructions. You start with the base image, you add whatever you want to add packages to that, you want to add user to that, and then use that image to fire a container. In Dockerfile also we did the same thing. In individual commands also we do the same thing. There is no difference, Sonali. There's no difference between the two. Maybe you and I can chat a little bit more, towards the end of the session. I'm okay to spend some more time and we can chat about this a little bit more, so that way, it'll be clearer whatever doubt you have. So we can do that, not a problem. Okay. So we've seen so far that Docker helps you run Docker containers based on images. We did that in two hands-on exercises using individual Docker commands and also using your Docker file. So however, in order to have your full project ecosystem running, or even to have the rest of your DevOps processes running smoothly, you should also know how to, name and store, version, and manage your images, and also be able to find your images. So a Docker registry is a service that provides Docker images on demand, and it's a centralized location basically that can either be public, it could be private, or it could be even a combination, which easily integrates with the Docker command tools. And when you're deciding on a Docker registry service, some of the things you should consider are how it will be used in your processes, the retrieval performance, the storage performance, any security issues, should look at all of these when you are deciding on the Docker registry service that you want to use. So yeah, this is the same diagram we saw earlier. So look at it something like this, when you're working on a project, when you're working on a software development project, you will create your own images, right? You'll not always be working on a base image, so you can use a public registry for all your base images. However, any customized images that you create, you can use a you can create a private registry within your office network that your entire project uses, you use, or any other project that wants to work with you will use that. So you could use a combination of different kinds of registry, and Docker Hub is a public registry that is available to everyone. So it is your default registry that Docker provides. Why does it move? So here you see the image tab is Nginx 1.9, which basically is the 1.9 release of the Nginx web server system saved in a Docker image. And because this is the default registry, the image may also be referenced by only Nginx 1.9. Okay, and depending upon the need, images and image versions can be distinguished by a major or a minor, and the point release numbers with default automatically be latest of any particular series. For example, if 1.9 is the latest version of Nginx, then simply saying Nginx latest will return the same version as we've seen previously in some of our examples. Then you have something called labels for your images. Labels are essentially used to distinguish images. They are like, they look a little bit like URI structures you see here, with the component of the naming system separated by your slashes. And the label should include the fully qualified domain name, which includes your name server, your namespace, any user organization name, any repository name, you know, and this final tag includes either a version number or a descriptive label. The net kernel SE could be the name of your version. So this is a URL for image stored in Docker Hub system, and it's a user image because of /r namespace, and the image itself is Databliss netkernel SE. Some other Docker registries could be. So Docker Hub is not the only Docker registry. It is a popular choice since it's considered the default registry, and it provides the highest visibility to public of contributed Docker images, and anyone can contribute to this. So if you decide to take an open source project and want to work on that, and made some improvements and additions to that, you can go back and put it back in the Docker Hub public registry for everyone else to be consumed. And that's how most of the open source projects happen. So the business model behind this registry basically allows one free private registry and any unlimited number of public repositories. So clearly, that means the Docker wants this community to function well as an open source also. That's why they've made it available. Some other options include the Google container registry, which uses your Google Cloud storage as repository for storing images. And then you have your Amazon EC2 container server, also available as part of your Amazon AWS cloud. And then you have Key, It's an example, it's a company that offers both free and pay for plans registries. And then of course, lastly, you can create, run, and manage a private registry of your own. So a very highly recommended strategy is to configure an automated build, uh, associated with the registry, and this can be done by associating your Git repository with the registry. So essentially, what happens is that every time you check in an updated Docker file and its corresponding build directory uh, into your Git server, this will automatically kick off a automatic build process. So it's a great idea, for your DevOps workflows, as it removes any potential error-prone human steps in this entire process. So remember, we were earlier talking about adding our Docker file to our source control system. So this is basically what it says. Once you have your Docker file and all the associated files, you can link it to Git, and it can help you trigger automated builds. This is kind of a workflow of Docker Hub repository setup. It's pretty self-explanatory. You go to the hubdocker.com website, create a new user, log in, you create a repository, choose a namespace, or or it be your username. Give the repository a name, short description, long description, sets its visibility to public or private, and you go ahead and hit create. And this is something you all can try. This is available for all of you to try on your own. So next is using your Docker Hub repository. So to use the Docker Hub repository from your command line, you should use the Docker login command and provide your username, and then you'll be prompted for a password, which you can enter, and it'll be stored as a hash form on your local computer. Uh, Then, images need to have the same name as your repository. You can create a container from that image. You can commit the image to the Docker Hub registry. You can create a new tag for that image. Images can be pushed into repository as well. So these are some of the commands to do that: Docker create, Docker commit, and Docker push. Okay, these are the commands that help you create images, commit, and push the image to the repository. So again, image tags can be viewed on the Docker Hub website. Uh, Images are retrieved using your Docker pull command. You've seen this numerous times, and this is your image tag. If you don't mention a tag, it will automatically pull the latest. Then we have deleting images. Can delete images. Docker Hub, however, doesn't allow you to delete images only. You'll have to delete the entire repository. So keep that in mind if you're going to be deleting your images very frequently. If it's very early on in the project and you're going to be creating and modifying and deleting images, keep that in mind if you're playing around with Docker Hub. Why images have to be the same name? Or well, images have to have the same name as the repository. This is how Docker Hub works. What about Azure? All open sources let you have some kind of Docker registry. So all open source cloud environments. Then Yeah. Next is your private registries. You can have, if you are basically, if you are in a project where you are modifying an image very frequently, when you're in the process of creating an image and you're modifying it very frequently, yeah, because you are building it, you're testing it, you're then using it to kick off a container, seeing if this is what you wanted, then you go back, make changes. So at that point in time, it's preferred to have a private registry, a local private registry of your own. That will certainly reduce the time to upload and download the image every time you want to create every time you want to trigger a container. And since it's a work in progress, like we said, Docker Hub doesn't let you delete an image. You have to delete the entire repository. So till the time you know that, okay, this is the final version that I am going to have, it's a good idea to work with a local uh, uh, private registry of your own. And any situation where you have to allow teams to share images locally, you're not the only one who are working on it, and you have a lot of team members. There's a need for you to upload, download very often, and store image specific to a project life cycle, say development in UAT. So since this is all uh, work in progress stages of a project, you can have a private registry at that point in time. And yeah, of course, you'll get the guarantee that the registry will be available for as long as you want it. And the different images under one repository can then have different names. You have to have one. You have to have. Of course, they can. You can. Wait. Let me go back. This is an example. Why did you go back? If you have a Docker Hub repository name ending 1.9, you will have 1.9 image in that. You'll not have 1.8, you'll not have anything else in that. So you'll never have 10 different images under a particular repository name. You have to name your repositories that way that it's easy to use for everybody. You'll never have this situation, Shrikant. You'll have different repositories for different images because every image represents something. It is not a file that you're putting 10 files in a folder. It's not that. An image is a representation of your working environment. If you have 10 different working environments, you'll have 10 different names for them. You'll have 10 different repositories. You'll not have one repository and 10 different images. I mean, how will people ever fetch that? How will people know how to get that? If you look at this particular path, this has to be unique for uh, each of your image. So we were talking about private registries here. So how to create a private registry? Basically, you do a Docker pull registry. We've seen Docker pull command before. So this is the easiest way to create a private registry. You can use a pre-built Docker container. And this is the command. You'll use it to pull. Running the registry. So the registry image that you pulled now can be run as a container. It needs to be run as a daemon container. Your -p option exposes the container's port as a local port for you, and you typically use the port 5000 for this. So this will be your command, docker run daemon port 5000 local of your to map to port 5000 of your daemon container. Name is registry from registry, which we pulled in the previous slide here. So now let's look at how to use the Docker registry that we have running on our local computer in a detached mode. So remember, its internal port 5000 has been mapped to external port also 5000. And in our earlier slide, we first pulled new image, Alpine, from Docker Hub. It's the Alpine Linux distribution. Uh, Again, this is a very small Linux that serves as a base for many custom images. Once you have this image stored locally, you'll tag this image with localhost 5000 Alpine latest, which it basically sets it to be associated with our private registry. And finally, you do a Docker push, localhost 5000 Alpine. This performs the push of your image to your private registry. These are the commands to do that. Configuring your private registry that we have running in our local Docker container. And this can be accomplished in a couple of ways. And one popular way is to pass an environment variable setting to the internal context of the running Docker using your hash D switch. This, of course, will require that the environment variable is expected and an action will be taken based on its set value. And another approach is to directly override the registry configuration file that is located at etc docker registry config.yml and in the Docker container UFS. We can also override this file by performing an external mount command using a -v switch. This will essentially take a resource located in your running directory and map it onto and above the specified location inside your container. So this would effectively superimpose our external file on top of your internal file, letting you do any level of customization that you want. The approach to customization that we saw on the previous slide, has some challenges associated with it, and our complete override of the configuration YML file would basically mean that we must completely replace the configuration, and that means we probably need to know about many more details of the registry implementation. And our approach also means that the authentication and search has been disabled for that, both of which are probably not will not be so big an issue if you're running it in a very small local context like your office. In order to build registries, there's a Docker registry RPM package. It's available for later releases of Red Hat Enterprise Linux, Fedora, and CentOS. Of course, it can be installed on a full installation or in a container, and it's been written in Python. You can also install Docker registry package as standalone machine, and again install the Docker registry RPM using yum. You can make any changes to this particular file, and then you can run the registry as service. These are the commands to do that. You've installed the Docker registry. You opened this file in the VI editor, and then you've started the Docker registry service. So Docker registry package, it can also be installed in a Docker container, and it needs to be built on a suitable image, something like a CentOS. Uh, the registry, it can be run as a service, as most of your boot software is missing, and it's also not a good practice, as the container should ideally run as a single application, and you'll need to write a script to start the registry, and this is the kind of script you'll need to have in place. So again, this is a workflow of installing Docker registry program in a Docker container. All the latest CentOS release registry layers can be added manually or by using a Docker file. You can install the Docker registry RPM, or you can optionally replace this file. You can install the start script and commit a new image to your repository. Next, we have running the container. So when you're running your new registry as a container for the first time, it's generally a good idea to run it as an interactive container with an attached input stream. This will basically allow the Docker container to come to life and allow us to access the internals of the container. So we can look at log files, we can make any configuration changes, or anything else that we need to do. And if we do find that we need to make changes, then of course those must be made in our own line of code software development to properly capture them under any kind of source control that you guys are using. And here we see how to run a Docker container in an interactive mode, and then in a second terminal. On a host computer, we issue your normal Docker registry command, your search, your push, and search. And we should also be able to monitor log files and in our first attached terminal. Okay, we have an exercise to demonstrate how to create and use a Docker registry. This is search command. Search command basically searches your image in a Docker registry. Any other questions on Docker configured by the command? Which this is a Docker run command. Basically, you've pulled the Docker registry and now you're trying to launch it. Remember, registry is a service. Unless you launch it, nobody will be able to access it. Any more questions? So this particular exercise, I want you guys to do it as a homework because it doesn't use any new commands. It uses all the commands that we have used in our previous two exercises, the Docker commands, and you basically need to create a Docker registry and do a few set of commands on that. It's very similar to all the commands we have done in the previous labs. So this particular exercise you all will do as homework, and tomorrow we'll uh, go through this quickly. If you have any questions, if you're able to do it, or anyone wants to discuss this further. Let's do a knowledge check question at this time. How can you determine which repository an image comes from? The repository location is contained in the image label. Lastly, we have Docker machines. So Docker machine is essentially a collection of tools, and it basically has a client that is used to access and control all your external or remote Docker hosts, which themselves could be standalone, or this could be virtual machines, or these could even be, cloud engines. The Docker client that way is quite powerful, allowing for control of even Docker daemons. Until recently, the native Docker was only available on Linux prior to version 1.12, and running Docker on Windows or Mac required the daemon in a full VM. So basically, there are two main use cases for you to use a Docker machine. The first would be to, if you have to provision multiple remote Docker hosts, and the second is to run, if you want to run on an older Windows or a Mac operating system computers that do not support the new native Docker implementation. So that's when you'll need a Docker machine. So as we saw earlier, Docker machine refers to a collection of tools that consist of your Docker daemon. Why do you change? Yeah, so your Docker machine usually is a collection of tools that consist of your Docker daemon, your REST APIs, for remote communication, and a corresponding client which uses the REST API to communicate with and control the Docker daemon. In order to install your Docker machine, it can be installed on a local machine. It has its own command line client, and it also has a regular Docker client, and it allows your Docker engine to be installed and run on remote machines that you're trying to manage here. So this is a diagrammatic illustration of Docker machine. So on this side, you see the client machine, and it has your command line Docker machine, and as well as command line tool called Docker, and then this use REST APIs to communicate with one or more remote machines that are running the REST API server, and of course the Docker daemon. This is an example of how you'll use it in a real work environment. In order to do a remote installation, while working with the Docker machine and a secure version of Linux or SE Linux, it was some issues were found. So some of the SE Linux security settings must be relaxed to allow for the remote installation of Docker. While there's support for SE Linux in Docker, there are certain known problems, and it's best to wait until these are resolved in a future release of Docker, and ensure any firewall rules don't restrict connections to port 2375. That is the port on which your Docker machine listens to. So first we must set up a separate user to perform your remote installation. Is the Docker machine same as a Docker toolbox? Yes, kind of. It is the same as Docker toolbox. So in order to do a remote installation, first you need to set up a separate user to perform the remote install. Then the remote user must have sudo access without any password. And you can also achieve this by editing the etc sudo users file and grant no password access. This is the way you do it in this etc sudo file. So next, we set up the remote user to use SSH access with no password again, and you'll start by generating your SSH keys on your local client machine, and then the client public key located locally in your SSH till the ID RSA file connected to the remote machine's file authorized keys. And of course, you'll want to test the connection to make sure your SSH communicates properly. We did this in our last lab, so you guys should be understanding what all this means. We did a hands-on lab to establish a SSH connection. Installing Docker remotely. So the Docker machine has a generic driver that will install Docker, and it works on all its supporting operating system. It requires the driver and remote IP address, and it of course also requires a remote SSH remote user and your local private key in order to make that connection for installation. It requires a name. So next we do is check our installation, and there are some steps that you want to make for detailed analysis, but fundamentally this is your Docker machine ls command. Uh, it works and lists all your remote installations, and then also checks that everything is working correctly from there. Next is Docker machine drivers. Uh, Docker machine has a whole bunch of drivers for installing remote instances, and most are for different cloud implementations, AWS, GCP as well. And most of your drivers allow instances to be started, stopped, your usual activities that you do on your Docker instances. And your generic driver for installing on remote hosts uh, does not do that. And some of the common drivers are Amazon Web Services, Amazon EC2, and GCE, Google Compute Engine. Uh, a lot of major Linux distributions are not fully supported. For example, the CentOS install is missing critical boot script. So these are some of the issues, known issues uh, with installing Docker machine uh, on these distributions. What security issues can affect Docker machine operation? We have a knowledge check question. The answer is D, A and or B. This brings us to the end of this lesson on Docker. So these are some of the things we learned in this lesson. Virtualization, benefits of virtualization, um, enhancements to Linux kernel, Docker, what is Docker, Docker images, what's the base image, how are other images created, how you can build on top of a base image, and by adding layers. Registries, what is a Docker registry, how to manage Docker registries, repositories of images, and Docker machine that allows Docker files to be installed and managed on a remote machine. So this brings us to the end of this lesson. Give me a minute while I pull up the next lesson. So our next lesson is on software development tools. So we'll in this lesson, we'll basically understand how to manage changes by setting up and using a source control system, and differences between popular source control tools, CVS, SCN, Git, and how to automate the process of assembling software components, and how to automate the building of whole systems using CI tools. So a large focus of DevOps is defining and managing processes such as your code development, code deployment, and your code operation. The tools we explore and discuss in this topic are all management and automation tools that are focused on reducing the workload on a DevOps professional. A lot of these tools are automated or allow you to automate a lot of your tasks and processes. So basically, these tools help you answer how do I build or rebuild a system that represents its configuration at a specific moment in time, and why is that important? It gets to be it gets to repeatability. If you want to have confidence that your processes end up giving you complete and repeatable control of the generation of software system artifacts. You all must have used some sort of source control system in your work or in your projects, and you guys coming from a slightly traditional way of doing things. Code deployments used to be manual process, but nowadays we have a lot of software that help you do automated deployments, that are linked to your source control systems like GitHub, and every time you make a change to your Git repository, it triggers a build creation and a subsequent deployment of that build to the environments that you want it to be deployed on. So we look at software that automatically let us do this. So in this, we'll look at source control systems at a high level and see how tools have evolved over time. And then in the next lessons, we'll explore specifics about some of these popular open source source control systems. So fundamentally, these tools help you manage your source code, your documentation, and any other project-related artifacts. Anything that is related to the system that may change is a candidate that goes into your source control system. And these also allow for version management in a source control system. So let's begin with the question, what is source control system and how does it relate to software development and specifically to DevOps? Though you guys all probably would have used some sort of source control system, but for this particular lesson in this topic, this is where we'll begin from. So a source control system is essentially focused on maintaining the state of all artifacts that comprise a software system. And when we use the word state of artifacts, we mean while each artifact, may be going through changes, you're writing your code, you're updating code, you're fixing bugs, you're updating documents, you're making corrections, you're deleting stuff. We still want to have a way to produce the complete set of artifacts at a particular moment, because at that moment there is a consistent, set of information. Your user stories, for example, your architecture diagrams, your unit tests, and of course your code, for example. They all should reflect a consistent view at any point in time during your project. The user stories should exactly match the work done along with unit tests, and the unit tests uh, should relate to the current set of source code. And as you can imagine, for a large set of artifacts, it's nearly impossible to do it if we, for example, could be talking about thousands or even tens of thousands of artifacts, keeping them consistent, uh, manually or, through some kind of manual tracking system is impossible. And because there's always change going on, there's always some work going on somewhere, somebody's working on something or making changes to something. So source control system allows us to, do that. It allows us to take a picture of all the artifacts and remember them also, depending upon which state of change, which stage of change they are at any given point in time. And even better is that each captured of state can also be given a label. You can give it a name, and for example, we are release one, build one, successfully completed. You can even label your state to build one, and that way this was the state of the code or documents of all the supporting artifacts when we had a successful build one for this particular software system. um, so by doing this, anytime you want to recreate the state when you did build one, you just go to that particular label, and once you'll get the latest code from that label, you'll be able to create that state in any number of environments, in any number of computers, in any number of developer PCs, or any number of environments, your test environments, your integration environments. This is indeed a crucial feature, as it allows us to go back to that exact state that matches uh, that particular label, or especially when you are in production, it helps you go back to the exact state that matches your production system. And if you discover an error in your or a bug in your production environment, we need to fix it, then we must go back to that exact set of software code, test case code, documentation, that represent that running system which is in your production. Once you fix that defect, once you fix that bug, all your artifacts, not just your source code, all your other artifacts will also reflect that. And then it will again be updated back into your source control system. So a source control system will basically manage a state of files in an operating system's file structure. Any type of files, could be text files, your source control files, could be your binary files, images. Revisions is again a very powerful feature that source controls provide us, and they basically keep track of revisions of your artifact. You started with a file version 1.0, and then you modified it to 1.1, then you modified it to 1.2, then you modified it to 1.2.1, and then you modified it to 2 maybe. So these are basically revisions to your artifact. And from the perspective of a single artifact, these systems keep track of their state as it changes over time. It doesn't make sense to keep track of every change used to change an artifact, because the state is in transition, and the user may make changes to an artifact during a work session, and when it has been brought to a new consistent state. The user may want to record that milestone, and then the user can communicate with the source control system and say, I want to check in to your repository the current state of this, particular document, which is, 2.0, for example, or whatever makes that particular state significant. If even 1.2.1 makes it significant, you can go back and check that in as well. So the source control system will basically capture the state, the username, the the current date and time, and as well as other meta information, and combine these as a type of save point for you. And depending upon the specific technology of your source control system, a version number may be assigned into that checked in file that you have checked in. The latest version of a document is often referred to as the head or the latest version, and it is the responsibility of the system to remember and maintain all your previous versions for that particular document or for that particular artifact. It kind of becomes clear when we look at the process of adding and updating artifacts. If an artifact needs to be removed, then the developer can simply remove it from the file system. But this is not going to remove the previous versions already stored in your source control system. So remember, a critical benefit of source control system is also its ability to restore a complete project to an exact state. Let's say the state that created release 1.2.1 of a system. And if that state relied on a particular artifact that later you deleted, it is still critical that it be returned if you are trying to recreate that state. Therefore, the system will retain artifacts that are retained, later removed from the file system even. So usually this is not a problem. However, if a deleted document contains a password, that is important to remember, that the password can be recovered by instructing the source control system to rerun things to the day when the password was a part of an artifact. So these are some of the things that are beneficial, but then you need to use them carefully to take the full benefit of that. So source control systems store their historical versions in a structure called repository or repos for short. These repos are structures that must be explicitly created and named as well. They consume resources, usually disk space, and a repo may correspond to a single file system directory, a system artifact such as a library or a subsystem, or even a complete system. Why not? And repos should have low coupling between other repos and a very strong cohesion within the repo. And we'll look at more of this. So these are some of the different types of source control systems that are there. So these could be file system based, these could be client server, and these could be distributed. And we'll look at each one of these in detail in the next slide. So the earliest example of source control systems were designed around the local file system that existed on a computer. And they would use a subdirectory of the target file system as the repository. And then these subdirectories were named after the source control system itself, and used to be symbolic links based to a shared directory or a network drive. It was usually through the symbolic links to a shared location that sharing of state happened. And two examples of these early systems are SCCS, Source Code Control System, which was part of Unix operating system, and Revision Control System, RCS, which is a GNU project. GNU is not a Unix project, by the way. Some of the implementations of file-based source control systems if you look at these early systems, it looks to be very primitive by uh, how we do software development today, and what source control systems today can do for us. So these basically worked on a per file basis, wherein each file state from original state through all its changed states was represented in a single file that used to be hidden in the subdirectory. So this single file contains special markup embedded in the file to capture changes or additions or deletions that got made to the file. And given the time when these systems were designed, they were probably uh, appropriate, as the storage requirements were considered very low. And you can picture a single file that starts with the original state. This is how it looked, then this got added, then this got added, then this got removed, this things like that. And then it contains what are called deltas, the actual full state of the file at any check-in point, then used to get constructed by starting from the original, then applying all the changes on top of that, all markups in the sequence that were listed in this file, uh, till you get to the end, and that's how you used to get the full state of the file at any given point in time. So the design trade-off was to favor CPU usage to reconstruct the file. I mean, it doesn't matter if there are 1,000 entries. We'll build it 1,000 times and build the state of uh, that particular document. And so this design basically minimized disk usage uh, at the expense of CPU time to reconstruct the state. It was not a bad choice if at that time, if the state did not change very often. However, there were other problems. Each file would uh, have its own version number depending upon how many times it was changed. So you could have a project directory structure, with so many files, whereas one file changed 20 times, one file changed 5 times, one file changed 8 times. So these will have their different version numbers. So this file will have version 1.20, this will have 1.5, this will have 1.8, and so on and so forth. So at any point in time, um, there was no notion of a snapshot of state for the entire directory. There could be one of version 1, one of like I said, 1.8, one of version 1.5. So you had to take a lot of care to track the association of a build event with the versions of constituent file versions. So for example, let's call this version 2.0. If we were to do a build now, we had to manually log it in a separate file, that in order to do build 1.0, file A had version 1.2, file B had a version 1.5, file C had a version 1.8, and file D had a version 2.0. So this had to be manually, or some manual way, or in an Excel sheet or on a paper. It had to be maintained that in order to create build 1.0, these are the different states of the files that are needed for for you to create this build. There was no way for the system to tell you or show you what goes in build 1.0. You had to manually maintain that. So that, if you look at it today, I mean, it seems unimaginable. I mean, who will do that? Who has the kind of time to do that? And this opens a lot of room for error, because this is all manual. So a lot of room for error, mistakes. Anytime something doesn't work, sometimes anytime your build doesn't work right, you have to go back, trace manually to, okay, which file version did we get wrong, So all these kind of errors, all these kind of mistakes used to happen. So one technique that basically emerged from this was to encode the build information into a string in the source code. The source control files then could be compiled, and subsequently the string value would be extracted to inform utility programs about the version state of the artifact. So there was a little bit of an improvement, where your source control file started to have a version number against the build. This approach did work, but it was dependent on a lot of other tools and processes. I mean, teams used to have very strict process around what can be checked in, who can check in. There used to be verification and validation rounds before any check-in could be done. And honestly, there were very few people who were even allowed to do check-ins. So not like today, every developer can check in their code, whenever they reach a logical point. There used to be like one or two administrator kind of people who were even allowed to check in the code, because they used to maintain these kind of lists, and they used to maintain these kind of repositories. So it had to be done through a very controlled system, a very controlled way. Then you have your client server based. So a lot of the modern software control, source control systems that we use today basically move the repository from a local file system to a proper server that is managing your source control repository. The server then, provides network connection, uh, access to all the client programs that are running on individual computers. And with the server managing the multi-user access, it can apply, same policies to all kind of upgrades. And an example of this approach is your CVS, the concurrent version system. This was based on the RCS technology, but moved to a client-server configuration later. Uh, it's still used quite a lot, but again, if you talk about Git and all that, it still seems like old school kind of thing. And a more current example of client-server system is your this commercial offering called Perforce, and open source project called SVN. Uh, we'll look at these in detail in our subsequent slides. These are some of the issues around client-server based source control systems. The biggest being the file sharing issue. So once you move to an environment where multiple users are sharing files and making updates, you have to deal with the reality that one user may end up overwriting another user's changes. So the diagram here illustrates this problem, where there's a artifact A, and Harry and Sally are both working on it. So they both start uh, they both take a version of that. They both start working on it. So Harry brought it to a state A dash, and Sally brought it to a state A dash dash. There is check in, check out. Yes, yes, there is. Yes. Where does it say there is no check in, check out? Well, there is check in, check out in client server base, but this is one of the very common problem that happens with a client server based source control system, what we are looking at here. So once Harry has made his changes, he checks in the file here. And once Sally makes her changes, she checks in her file there. However, her file didn't have these changes, so she's basically overwritten the changes that Harry did. Okay, so this used to be a very, very common problem uh, with these client server based file sharing issue used to be a very, very common problem. So people had to, manually manage this. Project plans had to be made in a way that, where a particular module is being worked upon, or a particular library is being worked upon, who are the people who will be working on that, and they had to work very closely, in very close conjunction, with each other. Otherwise, this used to happen very frequently. One or the other developer would overwrite the other person's file, and then they'll have to sit together and manually merge the changes. Yeah, some of these things probably would even sound foreign to you. Who manually merges code changes? No, the example shows that they both checked out. I mean, this is not the checkout check-in kind of scenario. They both took the latest version of the file. They made their changes. They added it back to the repository. He added it back to the repository. He overwrote the file changes that she made. So yeah. So some of the approaches basically to coordinate changes, and this is something that used to happen. So these are two fundamental ways to solve the problem of user update conflicts and lost updates. So the first one being lock, modify, unlock, and the other one being copy, modify, merge. And we'll look at these in detail in the next slides. So this is a very good diagrammatic representation of lock, modify, unlock, and you guys can compare it to the earlier example slide that we saw. So it's the same repository A. Harry reads it, and in order to make his changes, the file is now locked. Only Harry has access to make changes to this file. Others in the team can read this file. They can, but they'll not be able to make any changes to this file. So in the meantime, if Sally tries to make changes to this file, she'll not be able to because it's in a locked state. So once Harry writes his version, then he unlocks the file, he releases the file, and then anyone in the team can go back and work on this file and make any updates. So this is one way of doing it. Again, some of the issues around that is locking can at times cause administrative problems. User can lock a file and forget to unlock it, or worst case, go on a holiday, and then the whole team is waiting and watching how to start working on that file. And in that situation, you had to get an administrator to break the lock, which causes delays, and which can also cause loss of work that this user was last working on. It can also cause that, or the work that this user was doing is only half complete, but the lock has been released now, and another user tries to work on that file, and since the earlier work is only half done, it could lead to coding issues, compilation issues, and things like that. And locking was, kind of a false sense of security in many ways. So two users change different files, which are dependent. These changes can break the functionality. So okay, you're not working on the same file, but you're working on two related files, and you've made your respective changes. It can potentially break the overall functionality. And again, a lot of communication, a lot of coordination, developers, working very closely with each other used to be the way to take care of all this. And this was a lot of management overhead, used to be a lot of, I wouldn't say communication overhead, because communication within teams is always useful, but this used to be the kind of communication that actually ended up being a overhead. You had to know who all other four people are working on the same thing or could potentially be working on the same thing, and make sure that you all know what you all are doing. We even used to have a point where one developer would write one method or one function, another one would write the second, and then they'll go back and try to merge all of those so that the whole thing comes together. And yeah, all kind of workarounds and all kind of strategies we used to apply to this. So the other one being copy, modify, merge. And again, let's look at this particular diagram. It's a good. So two users basically copy the same file, and they both begin to edit their respective changes. And she goes back to publish her change. So the file is updated from original state A to A dash dash. And now if Harry will go back and try to write his changes, he'll get an out of date error because the file is not in A state anymore. It is in A dash dash state. So this would mean now he'll have to manually merge his changes into the state of the file, or he'll have to again take a copy of A dash dash and redo his changes on top of that and then write it back. So again, it was slightly better than the earlier state. Again, had its own set of challenges. So as we saw in the previous diagram, your copy, modify, merge does not allow commits from an out-of-date private copy. So either a fresh copy must be checked out or the private copy must be updated with a merge. And we have a diagram again here. So two users copy the same file. They both begin to update. She writes and he tries to write. He gets an error. He cannot write anymore. And another instance could be Harry compares the latest version to his own version. So he copies the updated file, manually compares, and creates a new merged version himself, and then goes back and writes this version to the repository, which now anybody can read. So this is the kind of example I was earlier explaining. This is how synchronization used to happen. Again, a lot of manual intervention was required, needed. So we saw a couple of conflict scenarios already. If when two users changes overlapped, this was called a conflict. So basically, you're working on the same file. Okay, you're making different code additions or modifications, but you're basically working on the same file. It's called a conflict. When the second user merges, the conflict gets flagged out, and resolving these is difficult, especially in large software applications programs I've seen. Uh, it it gets difficult at one point in time. It gets really difficult. Softwares cannot do these merges automatically. Some softwares used to start doing merges, but then somebody had to manually go and review that merge. You could not rely purely on the software to do your merge because there could be syntactical errors after that merge. There could be, compilation errors after that merge because you're basically trying to merge changes made by two users who, in their respective change, have done it all right, but they're not aware of other person's change. So, when those two codes get merged in a single file, unexpected things can happen. Again, these had to be manually resolved with discussion, copy, modify, merge advantages. Some of the conflict the advantages outweigh some of the conflict problems. So it's easier resolving conflicts than waiting for locks to be put in and then released, and uh, bringing in an administrator to release. Yeah, so this is the worst scenario, that the conflicts are so bad that you cannot just sit together and merge the changes. So you have to basically discard one set of changes, take the other person's changed file and apply those changes again on top of that. Or, the merge used to get so complicated that it used to be easier to, do one set of changes again on top of the other person's changes. So a tag is essentially a placeholder marker in your repository that flags the state of an artifact in that system. So one way to implement a tag is to have the source management system take a full snapshot of the repository and give the entire snapshot a tag. Like, once you have your production, uh, or even before that, once you have your UAT sign off, you can take the entire repository and give it a tag, UAT done or something like that. And again, tags are important for you as a DevOps professional. So it is highly recommended that repositories are tagged, and they are tagged with the release number of the software being built. And it's usually recommended to tag the repository, before you create the build, so that you can always go back to that state of the system if there are any problems with the build, or if there are any bug fixes that need to be done on top of that build. Next, we have branching. So again, your source control systems have different lines of development. They're also called branches of development, and the process of creating different lines of development is called branching. So you always start with your main branch. It's called the main, or it's called the trunk, or it's called your version 1.0, depending upon how you want to name it. So and all subsequent branches are then taken out or derived from your main or your trunk. So let's say you have a new uh, software being new software system being coded. So you start with your main, and you've done uh, a couple of months of work, and you're doing your sprints, and you're checking in the code, and then uh, you find out that there are a couple of change requests. Now, these are minor change requests, but you don't want to disrupt your main development branch. So you take out a branch, a code branch out of that, which is a child branch from your main. So it'll have all the code changes that you've done till a particular date in your main. And on that, you'll do your change request. So you're doing your sprints. At one point in time, you find out, okay, this is all we had to do. And here in this particular branch, your work is happening as it was supposed to happen. So from here, then you merge all these CRs, all these change requests that you did in the separate branch into your main, into your core. It is also called your core. A lot of companies also call it core. So it is a merge, it is a code merge on a working branch, but it is a one step merge. So of course, let's say you had 10 CRs here, and you did whatever you had to do with those in those CRs. Of course, you did some initial impact analysis of those CRs, and assuming everything was fine. So you did a merge here. So that was a one-time merge. Those 10 changes on, starting from between this state and this state of your main, fine, whatever was supposed to be merged, resolved, you made the developer sit down and you did that merge and then you moved forward. And the other state is, this is your production state, this is your snapshot in production from where you started. And you have one release that is starting. So you take out one branch from that and you start working on it. Your main still remains. Your main is always there. It doesn't go anywhere. So you start working on this particular releases code. And then you find out you have to do a small bug fixing release, for 2 weeks. And all those bug fixes have to go live because, some customer is screaming that they cannot live without this functionality, whatever, whatever. So you take out another copy of a branch from your main. So these branches are essentially copies, copies of your main branch taken at a particular date and time or a particular state of main. So you do your bug fixes, you make it live, it goes into production, then these have to be merged back into your main. And now from this state, it is your main plus these bug fixes. What is your new main? Okay, that's why I said your main will always be there. All these other branches that you take out from it, or it is also called cutting a branch. A lot of companies use the language cutting a branch, like cutting your tree branches, something to that tune. When this release is over, it has to go back and merge into your main once it's ready, once it's live or ready to go live. And subsequently, all other branches that you are merging back into main need to be merged into all other active working branches from main. Okay, so if this particular release went live, you merged it back into main, so this became your new main. This particular branch was taken before this bug fixes branch was worked upon, right? So now this is your new main. However, this particular code branch doesn't have these 5 bug fixes you made here. So if you'll merge this into main, these 5 code changes, 5 bug fixes will be lost. So this second branch, of course, has to be merged in main. It also has to be merged in your first branch. It also has to be merged in your third branch. Okay. Similarly, when this guy would go live, it'll have to be merged here. It'll have to be merged here also if this guy is still continuing and has not gone live. So anytime you merge into main, and only time you merge into main is when you are ready to go live or you have already gone into production. So anytime you merge into main, you merge into all other active code branches from main that are presently being worked upon. Okay. How about regression testing, if any, when a branch merges into trunk, if trunk gone through some tests already? See, your trunk is always your production version. Okay, in this kind of a scenario, what the diagram shows here, your trunk will always be your production version. If it's a fresh development, then yeah, your trunk could be would be a work in progress branch as well. It will not be a production branch, and in that case, the mergers and regression testing, everything will be tenfold complex. But assuming your trunk is your production version, so it would have already been regression tested, it would have already gone through UAT, and then only you would have gone live. However, you are right in asking this question in a way that when this, assuming you merged this guy here, and then you merged this guy here, and then this guy is ready only here to go live. So you already had 2 merges before that, right? You merged this guy here as well, and then you merged this guy here as well. Sorry, this here, not there. Wait, what am I doing? So the last branch to go live has a hell of time doing regression testing. I can tell you that from my personal experiences. Uh, all this has to be planned very carefully, Shrikant. That's the only way I can answer this question. This all has to be planned very closely, you know, very, very closely. I mean, you have to make sure if this bug fixes branch merged here and this guy came and merged here also, all the tests that you ran here should be in the test case of this particular branch after it has been merged. Yeah, they are confusing. They're not controversial. I mean, they are the way they are the way to manage your code and your code branches, especially if you have too many releases, too many branches of development happening. They get confusing. They are complex. I mean, I wouldn't say they are simple. They are complex and they require good amount of planning, and when which branch is being taken out, when which branch is being merged, which all branches it has to be merged in, what is the consequences of that, has the second branch shared their test cases with the first branch, has a third branch shared their test cases with the first branch, what will happen after you'll do these two merges to the first branch, will it break anything? It might break something, or you might have fixed a bug here and in the first branch you've completely removed that functionality. I've seen these kind of scenarios also. Then the question is, why even merge it here? Because the functionality is going away, right? So again, some of these are very judgment calls. Some of these are, calls looking at the whole system in itself. So it's not easy. It's not easy. It's complex. Once you understand it, once you start to get the hang of it, doing it then is not easy. Coordinating the activity is always complex, and I don't think there's really any easier way to do that unless software is completely take it over from us, which I don't know how and when it will be feasible. So basically, I explained you this whole slide by talking through this. I'm not going to go through each of these bullets now. And different teams do it differently. Different projects do it differently. Teams and projects come up with policies around when they'll, cut a branch, when they'll merge a branch. They have, a disciplinary list of tasks that all developers will do when they're checking in their code, so that the future branching and merging is smoother. We maintain different branches currently. Definitely, it's complex. And it does. I've unfortunately had the opportunity to work on products like 20 years, 25-year-old product source code, where it used to end up taking more time to merge the changes than to actually make the changes. I know it's a very sad state of affair, but it used to be that complex. It used to be that complex that it ended up taking that kind of time. And yeah, I mean, it was not fun. I can tell you that. It was not fun. So repositories as okay. Wait a second. Give how many slides we have on this. Okay, we'll finish this slide and then we'll stop for today because next topic is the distributed system. So we'll finish this for today. So repositories are basically your key tool for your DevOps management. They provide you with the mechanism to control your state of all software artifacts, and even in a very chaotic environment. And I just gave you a lot of examples of the kind of chaos. And once the artifacts have been committed to the repository, they are then stable. They never change inside the repository, and the repository itself will change as different commits are added. Uh, However, the commits, of course, themselves represent a progression of immutable state, and they are captured for all the time. And As you can imagine, with multiple branches and policies, repositories can become very complex, and branches and merges can indicate in very close relationships. For example, like examples we took earlier, bug fix on one branch is merged into several active release branches, and these relationships would make sense and are necessary. This is my chat window, so I have to keep it a little visible, but I've put it down. I know you guys can see it like a block, but yeah, this is your complete diagram. So again, you have to keep in mind all these necessary relationships between different branches that you have, and also keep in mind that history always flows forward in your repository graph. So and one last point, basically when a software experiment is started on a new branch and then abandoned for any reason, that will be represented as a unused branch. These branches can be deleted if the history and the results of that experiment are no longer needed by you. So yeah, this is again a diagrammatic representation of you started with trunk, created two branches, then you merged it. Oh yeah, similar problems on a larger scale. In this diagram, I can tell you it's on a much larger scale. Okay, with that, guys, we'll take a break today. And don't go, don't go. Just give me a minute. Am I okay? No, I'm not sharing. So we've had a good amount of question and answers. Uh, sure, Ritesh. Let me finish this and then we can chat. We've had a good amount of question and answers, and I hope everybody found it useful, beneficial to ask questions as and when you had them. And remember, you can use Simply Talk to ask more questions, questions regarding this course, questions regarding a particular topic, questions regarding a particular lab, and of course, you can use help and support from Simplilearn if you have any specific questions that you want to put there. You'll be given a feedback form at the end of the session. Please, please, please fill the feedback form. Like I told you last time also, this is our way of knowing how the course is going for you. And I think that is a very important thing. That should be a very important thing for you also, because you've taken the time out of your schedules to undertake this particular course. So please give a feedback on your today's session, and you'll be asked to rank on the trainer, the course content, the WebEx tool, and the Get Certified team. And you'll be asked to rate between 0 to 10. And we aim for a rating of 9 and 10, and anything less than that will be looked at by the Simplilearn team. Someone will even contact you to find out more details about what caused the dissatisfaction and how it can be addressed. And these are the different social media channels that you can find Simplilearn on. And I think we are done for today. Thank you, everyone. Please practice your lab before you come tomorrow, or try to practice before you come tomorrow. If not, definitely practice it during the weekdays. And thank you. We'll talk tomorrow.